Okay.
So is on the Cougar courses, it says it's due Thursday at midnight.
No, it's not due till kind of like the last week of class.
Okay.
That's when I recommend that you do it by, because it just gets busy.
I think
that's the due date listed though. Sorry.
Yeah. No, yeah, I was going to say the same thing. That's the due date that's on Cougar courses right now. Like it's only going to give us another 2 days.
Well, I'll change that then, because that's not right, because that's not the intent.
And then I also had a question. The numbers don't exactly match up on the Word instruction document and the Excel one, because some of the numbers are off, but basically as long as we answer all the questions, and then the last question, we're just explaining if our findings for the predicted exam score make sense. Is that?
Yes. Okay. Yeah, just an interpretation.
Okay.
Okay?
Okay, thank you.
So I'll fix that Excel due date.
Professor?
Yes.
I had emailed you a while back about exam number 2, asking if it could be open on the 18th to take. And you had said that you would open it for everyone on the 18th, but I noticed it's still not open until the 22nd.
That's exam 2, right?
Right, correct.
I don't understand that, because I did change that. You know what? Let me go check that right now, because.
Okay, I really appreciate it. Thank you.
Yeah. I thought that I did that. Maybe I forgot to save it or something. Exam 2. Exam 2 is down here a little ways. Yeah, it's not there. Well, it's open on the 18th. I don't know what happened, because like I said, I tried to open the 18th. So I thought I did that. I guess not.
Thank you.
Okay, it's done. I guess I could change the Excel due date that fast too. I can find it. Excel, project instructions, basics. It's probably in here, right? Oh no, the assignment. Here it is. Due date. Wonder where that comes in. Let's see here. Let's see, I need to go get a calendar and see what days. Good day to have it due. November, December. See, finals week starts the 12th. How about if I make it due the December 10th? That's a Saturday night. Anybody there? Oh, did I lose you?
Hi, this is Nicole. I just came in, so I wasn't quite sure what we're talking about.
Yeah, that's fine. He's talking about the Excel due date.
Oh, okay, got it.
So is December 10th long enough? I mean, it's the day after the last day of class.
I think so. I kind of just finished it last week. It didn't take that long, so.
No, it's an easy thing. I mean, it's not that hard anyhow. Okay, I'll just change it to December. Might as well make it a Sunday night as before. Enable December 11th. And I guess we better make it 23, 25, 55. Okay, done. Those things are all done. Anything else I can help you with? Anybody?
I was hoping we could go over chapter 10.
Sure. Sure, we can go over chapter 10. Do you want me to do the PowerPoint like we did last time?
Yeah, that'd be great.
Okay. Let me pull it up. Okay, I got that out, so I need to get this back. Share screen. That's the one I want to share. Can you see the PowerPoint?
Yep.
Yeah.
Yep.
All right, we're in good shape then. So we need to talk about 5 different things. The last one is one that I put in there on my own. Independent events, conditional probability, the multiplication rule. So just start going through it and see what happens, or do you have anything special that you want me to talk about? Okay, here's the rules. I will start talking, and your responsibility is to interrupt me.
Okay, sounds good.
Okay? That's what I tell my students. That's your job. Okay. So we need to know when events are independent. Are we okay with the concept of events?
Yes, I am.
Okay.
As am I.
Okay, good. So 2 events are independent when one event when one event occurs, it does not impact the probability of the other event occurring. So, for example, the easy examples, if I'm drawing a marble out of a jar, and on the other, with my left hand, and in my right hand, I'm drawing a card, a single card from a deck of cards, those events are independent. Because whatever I do with my left hand is independent of my right hand. Okay? And so, male, as I'm saying in this chart, male and brown eyes are independent. The fact that I'm male does not impact the percent of the people having brown eyes, and vice versa. However, male and taller than 6 feet are not independent, because if you are male, then it's more likely that you're 6 foot tall or taller. Male and high cholesterol, it's not obvious, so I don't know what the answer is, but maybe it's independent, maybe not. Male and pregnant are definitely not independent. If I'm male, I will never be pregnant, and vice versa. So these are not independent. These are dependent events. So does this last one make sense to you? The male and pregnant?
Yes.
The fact that I'm male will impact the fact whether I'm pregnant or not, and vice versa. Okay, good. Well, that's independent events. Okay, so this is another way to get independence. And I have this silly example here. I'm embarrassed by it, but so we have a population. Let's see, if I can get rid of this bar up here. Yeah.
I don't see any bar up there. So
Okay,
it's not appearing on our screen.
okay, well then, okay, that's good. It was on my side, I guess. But anyway, sampling without replacement. So I have a pond. Let's say I have an artificial pond with 10 male frogs and 10 female frogs. When I first think about it, the probability of drawing a male frog is 10 out of 20 or 0.5, right? But now when I draw the second frog, if I don't put the first one back in, then the probability that the second frog is a male is 9 out of 19. I've taken one frog out, and then one male frog. I mean, the frog I took out was male, so I've gone from 10 to 9 males and 20 to 19 frogs. So my probability now is 0.47, not 0.5. So without replacement leads to dependence. So if I'm doing 2 consecutive events without replacement, then they're dependent. Okay? Why didn't this arrow work? Okay. However, there's a bit of a conundrum here. I think that if I take my whole country of frogs, all the thousands and thousands of frogs that we have, assuming they're half male and half female, and I draw a male out of that whole country, I'm left with 0.5. The probability that the second frog that I draw out is a male is really, really close to 0.5 because the population is so large. So here the events are nearly independent, and in fact, they are treated as independent in many situations. Just something to be aware of. Okay, conditional probabilities reflect how the probability of an event can be different if we know some other event has occurred. So let's see what we got here. Well, there's a formula for it. Let's skip the formula for just a second. Let's look at this example. Here I have a collection of dogs. And I have a Dalmatian is hearing impaired for one event. And B is the Dalmatian is blue-eyed. And here's my sample space, a big white area here. And what I've been given is that hearing impaired, HI, and blue-eyed is 0.05. 5% of the dogs are both of these things, hearing impaired and blue-eyed. However, hearing impaired only is 0.28, and blue-eyed only is 0.11, 11%. So what's the probability of being hearing impaired if I have blue eyes? Well, the formula that you want to use for conditional probability is P of H given, okay, P of hearing impaired given that it's blue-eyed, the straight line means given, is equal to P of hearing impaired and blue-eyed divided by the probability of blue-eyed. So hearing impaired and blue-eyed is 0.05, blue-eyed is 0.11. So that hearing impaired given that it's blue-eyed is 0.45. You with me?
So far, I had a question about a quiz question that I think was related to this, but I don't know if there's other questions before we
jump in.
next. I don't know if there's other questions in regards to this or not.
Jump in. Let's hear your question.
Oh, okay. So, and it could be that I was treating the question incorrectly, but based on this question about the dogs, I thought that the question on the quiz might be approached in the same manner.
Yes.
So it was for a particular species of wolf, 55% are female, 20% hunt in medium-sized packs, and 15% are both female and hunt in medium-sized packs.
15%?
Yeah, 1-5. So 55% are female, 20% hunt in medium-sized packs, and
Right.
15%, 1-5, are both female and hunt in medium-sized packs.
Okay, so that means there's 10% that are something else. Because that only adds up to 90%. 55 and 20, 75 and 15 is 90%.
So is it, that's what I was starting to draw out, like the image that's on the slide that's showing. So I had, is that an appropriate way of?
No, that's perfect.
Okay, so I did like one circle was 55% are female. I did another circle that was 20% that hunt in medium-sized packs.
Yes.
And then the overlap area was 15%.
Perfect.
So then wouldn't that mean that there's actually 5% left in the
That
hunt?
are outside both of the circles?
No, so hunt in medium-sized pack. I guess I'm getting confused on that.
What was
So
the question?
So 15% are both female and hunt in medium-sized packs.
Right.
Doesn't that take away from the percentages of both of the big circles?
It doesn't take away from it. It is in this middle part, like here. That's in both circles.
Okay.
So if you look at this 5% in this middle area here, can you see them? So there's 5% here, but 6% only in the big one. So 5/6 of the big stuff, or this egg-shaped one, are in the middle area. 5/6 of this one are in here.
Oh, okay.
There's very few out there.
Okay.
23rd are here.
So then for the wolf question, since we add it up and it's at 90, then we know that the space outside of the two circles is 10.
Right. This 0.66 then is 10.
Okay, so that they're neither female nor hunt in medium-sized packs.
Right. Neither female nor hunt in medium-sized packs.
Okay, because then the question is the proportion of wolves that are neither female nor hunt in medium-sized packs is, but are
Males or?
The proportion of wolves that are neither female nor hunt in medium-sized packs.
That sounds like that's 10% to me.
Right. So then the only options that were given, though, were 45%, 80%, 20%, or 40%. So that's where I was.
Okay. Neither males. So not male and not male and not.
It's actually not female.
Right, not female, but that's okay.
Yeah.
But that's male. Male and not hunt in medium-sized pack. Right?
Correct.
Well, it seems to me it can't be more. The question so it uses the word nor. So I'm taking that to mean they're not male, they're not female. That they're male,
Right.
they're male and they do not hunt in medium-sized packs.
Right. I typed it in the chat window too, if it's easier to see.
That's. Oh, you have the exact question?
Yeah, the exact wording of the question I typed in the chat window.
Let me see if I can find the chat window here. I got to get out of this first. There it is. And that sure looks like it ought to be 10%.
Did anyone else get this question or get confused on this question?
I got this question too. I had a different set of answers, but I also got it wrong.
You had a different set of answers for it?
Yeah.
It must have been a slightly different question. I hope.
I think it was the same. Let me see if I can pull it up. I don't know if I can.
So I was at least approaching the question in the correct manner.
Yes, you were.
Okay. So it would be appropriate to do that diagram.
Yes, of course. Yes.
Okay. Okay, that's good to know at least.
Okay, my question was different.
Oh, okay. Thanks.
It was a similar question. It just had a different set of answers.
Oh, okay.
So I'm going to go back and change that one then. I'll fix that one. I've got a note here to do that.
Okay, so that was just a typo, so it should be 10%?
Yes.
Oh, okay.
So does this affect your overall grade? And you want me to change that?
No, it was just I haven't necessarily submitted the quizzes yet. I just was going through to see them.
Okay, I think I can change them in the middle of this because.
Oh, okay.
Yeah.
Okay, thank you.
Sure, no problem. Okay, next. Oh, you want me to continue this charts?
Please.
Yes, please.
All right, let me back up. Move forward a lot by accident here.
We were on the Dalmatian one.
Right.
It helps me to hear you go through it live so I can interrupt and ask questions when I don't understand something.
Yes, that is.
I agree, Karen.
Right. Okay. Okay. So conditional probabilities. This was an earlier chart than the Dalmatian chart, but we can go to it now. Conditional probabilities reflect how the occurrence of one event impacts another one. So, to use the easy example, if I'm male, I will not be pregnant. So the conditional probability of the probability of me being pregnant is 0, given that I'm male. But the probability of one of you being pregnant is not 0 if you're female. Okay? So there's a formula for it, and it's an easy one. The probability of B, of one event, given that an event A has already happened, is equal to the probability of A and B divided by P of A. Now, when I first took this class, I just had a miserable time trying to remember which one went on the bottom. But it's this last one, always goes on the bottom. P of B given A, so I divide by P of A. So that's just the formula for it, and then each problem that comes about, you have to just substitute in the A and B and the probabilities. Sometimes you will be given P of A and B, and then be given P of A. You can calculate this. You can also be given the left side, P of B given A, and this, and you can calculate P of A, and given any two of these, you can calculate the third. So we just covered independence. Two events are independent when P of B given A is equal to P of B. Now remember what independence said, it is that the occurrence of one event does not impact the occurrence of the other. So the fact that A occurs, P of B given A has occurred, the fact that A occurs does not change the probability that B will happen. So two events are independent if these two things are equal. It doesn't mean that P of A is 0, it just means that the occurrence of A does not impact the occurrence of B. Okay, then we have the Dalmatian problem. And this is the powerful rule. For any two events, P of A and B is equal to P of A times P of B given A. Now, that's for any two events, whether they're independent or not independent. And I had to pick up my dog, sorry. Now, the rule that is most often used is the multiplication rule for independent events. So if A and B are independent, then P of A and B is just equal to P of A times P of B. So if I'm drawing my marble from this can, using my left hand, so I have a jar of marbles on the left over here, and I have 10 red and 20 blue, 10 red and 20 blue. The probability of drawing a red is 1/3. Okay. Now, if on my right hand, I've got my deck of cards, and the probability of drawing a spade is 1/12. So the probability of a spade is 1/12. Well, those two events are independent. So the probability of drawing a red marble and a spade is just P of A, which was 1/3, times P of spade, which is 1/13. So this one's where it's used most of the time. You can also use it with if a person is playing a game, and let's say darts, and he has a 70% chance of winning at darts. Well, the chance that he will win at 2 games of darts in a row, P of A and B, winning the first game and the second game, would be 0.7 times 0.7. So there's a 49% chance he would win both games. So that's the way that the multiplication rule is used most of the time. There are times where you'll need it, like with the general multiplication rule. We just went through the frog example. Now there's the blood donor problem. So two people come in to give blood. Well, there's a 45%, 38 that's O positive, and 7 it's O negative. So 45 it's type O, and so each person has a 45% chance of being type O. The probability that the next 2 people coming in are both type O, assuming they're unrelated people, it's just 0.45 for each of them, so I can multiply them together because they're independent events. So that's about 20%. So that's how you use the the multiplication rule when events are independent. Tree diagrams are very, very powerful. So the probabilities of skin cancer among men and women are given. And so the probability of skin cancer in the area of the head is 15%, in the area of the trunk is 41%, in the area of the limbs is 44%. And so that adds up to 100%. However, if the skin cancer is in the head, there's a 44% chance it's man, and a 56% chance that it's woman. And if it's in the trunk, it's 63% men, 33% woman. So a tree diagram allows you to display the conditional probabilities. Because if you look here, the probability of a woman, given that it's head cancer, is 0.56. So the probability that given that it's head cancer, well, I'm in this line then. So I start here, I'm in this line, and the probability that it's a woman, given that I'm in head cancer, is 0.56. So I'm being able to take my tree diagram and use it to represent conditionals or to actually draw the conditionals from the tree diagram. Okay?
Okay, I get that.
Yeah, and I think that's it. So here's the disease thing. We have an individual comes in, and the individual has some symptoms that there's a disease. Actually, for speech pathology, you probably can have something other than disease here. You might have some speech condition that there's symptoms of. That's what you could use here. And so in our case, you would have disease and no disease. There may be symptoms, but you're in one of these paths. You do a diagnostic test, and you would do this probably in speech pathology. And the test will either come back positive or it will come back negative. And if it's positive, this is called a true positive, because this line, you have the disease and the diagnostic test came back positive. So that's a true positive. This one's a false negative, because you have the disease, but the test came back negative. So it's the negative part is false. So it's a false negative. This one below it is a false positive, because the test comes back positive. The diagnostic test came back saying you have the disease when in fact you don't. Okay. I think so. I teach the same course for nurses, and this is an important part for them. This is another example, or this is a concrete example of how it's done. And it's an interesting, let me just jump forward one little bit here. Okay, good. So this one, suppose about 1% of a large population has HIV. And there's an enzyme that has a sensitivity of 9985 and a specificity of 0.9940. Let's go back and see if we can figure that out. The specificity says that if it's negative, says that for my diagnostic test, if it's negative, if I don't have the disease, it'll come back negative with this %. And the sensitivity says that if I do have the disease, it will come back positive with this %. Now, as in general, you can't have, it's difficult, expensive, more than likely, to have a high one of these and a low one of these simultaneously. And I think you take some initial tests where you take where you reach a proper balance between these two, and that particular test is cheaper, then you might get into a more expensive test to make sure that you're in this, that if the test is positive, that you do have the disease. I mean, you want this to be high and this to be low. So this next chart just goes through some of these probabilities. So I've got 1% of the population has HIV. So if I put my one, so this first line is they have HIV. So 1% of the population has it. 99% does not. And I've got a sensitivity that says if I've got the disease, there's a 99.85% chance that it will come back positive, and a 0.15 chance it will come back negative if I've got the disease. So picture yourself going in with symptoms, and you come back with a positive test, and it's 99.85% sensitivity. And you ask, and so the question is, what's the real probability of having the disease? Well, it's not 99.85%. And if you go through some details, you'll see down here. Oh, well, that's the question still. So I just filled in the lines with the data that's been given to me. And the next chart is going to say the probability of a true positive is that a true positive is going to be, I have the disease and the test was positive. And if I go back to my conditional probability question or equation, that's going to equal the probability of disease times the probability of positive times disease. The net result of all that arithmetic is that there's really only a 1% chance, 0.99, a 1% chance that it's a true positive. There's a 0.6% chance, 0.594% chance that it was a false positive. So I don't have, there's still just a 1% chance that I've got the disease, even though the test came back positive. There's a lot of numbers there, but did the concept make sense? Nobody's.
I'm still struggling with this. Give me a minute to process.
Professor, this is Lauren.
Okay.
So there seemed to be a test question that's very similar to this. It was regarding women and cancer with mammogram screening. And it shows a tree diagram. And it wants to know the probability that she indeed had breast cancer.
Uh-huh.
And I'm so lost on it. Is there any way to look at that question?
Yeah, sure. Let me get out of this. This is on the question for.
It was the chapter 10 quiz.
Right, the chapter 10 quiz. Okay.
I can follow the lines of cancer and being positive, but there's the no cancer there's still a positive 0.1. And I don't know how to do the math.
Oh, let me get back to that then for just a second. I'll show you that part here.
I think I finally got it. It took me a minute, but I think I'm getting it.
Well, that's fantastic. So you still have this option of the test coming back negative but you have the cancer or whatever it is, the HIV. You have HIV, even though the test came back negative.
Okay, so on this tree diagram, the random adults, so you would take the 0.1, oops, oh, there it is, the 0.1, would you multiply it by that 0.9985 positive?
That's the probability of having the disease and having a positive test.
Okay, what about the 0.006 positive? What do you do with that number since it is positive?
Well, that's the percent of people that will have a false positive. So if you don't have it and you go in and the test comes back positive, there's approximately a 0.6% chance, it turns out. I mean, 0.006 times 0.99 is really close to 0.006. So
Okay.
you're going to still have a false positive. And there's a certain percent of people will think they have HIV because of the positive, but they don't.
Okay.
Professor, I took a screenshot of the question that Lauren's talking about, and I just emailed it to you.
Okay.
If you want to pull it up.
Right, because I'm using the same math as this current slide, and I'm still not really getting an answer for the options provided, so I know I'm not doing something right.
No, something, or there's another error.
It's probably me.
No, I don't know.
Lauren, was it the one that, because there's a couple of them that are all based on the same picture, but then it has different questions asking about it. So are you talking about the one that was, that just said received a positive test result? Or are you talking about the one, there was another one that said like,
Age group.
cancer given positive test?
Let's see. I think it definitely was that they indeed had the breast cancer.
Okay.
And then it had something about the age group.
So if a randomly chosen woman in her 50s.
This one's 40s.
Oh, okay.
Here, I've got some questions here. Can you see the screen?
We just see the slideshow still.
Oh, okay. Let me share the screen. Let me share. Well, yeah, I think that's the one I want to try to share. Might pop up different answers. So is this it?
Well, but the question I was looking at had the tree diagram, and I was trying to follow the numbers and do the equation of the P, disease and positive equaling.
Okay, let me go to my email. For some reason, I suspect that I'm not getting the tree diagrams with this process, but let me try one more.
It was the incidence of breast cancer right there. Down one. Yeah, right there, that one. Is this the specific question, Lauren, that you are struggling with?
It is the same tree diagram. However,
different question.
Yeah, the question was talking about the PPV for an age group of women in their 40s.
Well, we can just go to the next question. It's probably.
Oh, here you go.
That one's a false positive.
There's more. Oops, not there, here.
That's not it either. It's the age group. It's
There's a 40s.
definitely right, but there was like it was a longer question, and it was talking about the age group and wanting to know about the age group. Yes, that one.
Oh, okay.
Okay. So 1.5% have cancer, 98.5 do not. 80% will come back positive, 20% won't. 90 and 1. If a randomly chosen woman in her 40s, taking a mammogram scanning test, gets a positive result.
So what were you doing, Lauren?
Well, I was kind of thrown off by the whole age group thing. I was taking the 0.0149 because that was cancer. And then I was looking at the 80% positive, and I multiplied them, but I don't know if I'm supposed to do that.
That's what I would think.
And I don't.
I think that you have to, I think it goes back to that conditional probability equation where it's P of B given A, and then you take P of A and B and then divide by P of A. So if you do the probability of cancer and positive test, which is what you were doing, the cancer 0.0149 times 0.8, but then you divide by positive test. Is that right, Professor?
Yes.
What the positive test would be?
Well, there's where it's tricky.
Okay.
Because you get a positive test here.
Right.
And
a positive test there. So the probability of a positive test here is 0.8 times this number.
Mm-hmm.
The probability of a positive test here is this times this. And you add those two together.
To get your denominator?
To get the denominator.
Okay.
So you would have 0.8 times 0.149 divided by 0.8 times 0.0149 plus 0.9851 times.
Okay, so it would be A 108.
Perfect.
Okay, I got it.
Well, that's good. I mean, that's a good thing. So
Okay.
this doesn't have to. I mean, so when you've got a list of things here, what you want to get the final list of outcomes. You just see which outcomes that you want to pick out of these and add them together.
Mm-hmm. Okay.
And this is a very good example of Bayes. This is how you do Bayes theorem. Okay, so let's see. I think we're almost done with the slides, actually.
So it seemed like it was just the confusion of the fact that you had to add those two portions of the positives to get the denominator. Okay.
Yeah, I think I got confused by the no cancer, like the false positive really confused me.
Right, and how to actually include that information. Yeah.
Okay.
Right. So you include it because there's two ways to getting positive.
Mm-hmm.
And it just says positive test. It doesn't say.
Right.
Yeah.
False positive.
Right.
Okay.
So if you had multiple branches coming down here and there were more ways to get positive, you would just add them all together to get the final total positive.
But the only reason we had the 0.0149 times 0.8 as the numerator for this particular was because the question only says cancer given positive test.
Yes,
So that's why we only included those two parts.
right,
Okay.
right.
Okay.
Um,
But then it just says positive test for the given or for the denominator part.
right, and so you just
Okay.
need positive test. So who is speaking?
Sorry, this is Nicole.
Nicole, okay. Good explanations and good questions and good answers, both of you.
Thank you.
Thanks.
They really are. I mean, it's always fun to get these, to me, you know. So I think, let's see, where are we? Yeah, we got one more chart. Oh, we looked at this chart. Yeah, that is the last chart in the series. So that kind of covers those charts for chapter 5. Chapter 5, chapter 10.
Okay.
I'm looking at the number and I see a 5 up here.
Thank you so much for going through that. Going through it and hearing the other people talk and ask questions and processing it really helps me understand it better.
It helps me too. I mean, that's just the way to do it, you know. I mean, it's fine. I just don't. I'm never quite sure this process of online math courses work, but we're trying. So,
I almost wish sometimes that you had like a whiteboard behind you or something that you could like, because we can see your face. So like if you had like a whiteboard or something, I think that would sometimes be.
well,
But it works with the sharing screens and stuff. I just think sometimes I wish you could just like we were in a live classroom and you could just draw it out for us.
you know, I wish I could too. I bought an Apple product that kind of allows you to do it, but so you could, you know, so it was software, and I could take this fancy pen and write on it, and you would see what I wrote on my iPad on the computer screen, but the pen was so thick I couldn't get anything readable. I mean, it was just awful. So I had to give that up.
Can I go back to that tree diagram we just discussed about
On the question?
Yes, please.
This one? Can you see it?
Yes.
Okay.
So okay, I understand now that the true positive is 80% of cancer.
Yes.
And how would you find then the percent
What percent?
of women that actually do have like true cancer?
The percent that have cancer?
Yes.
It would be the percent. Well, the answer is simply this. It's 0.0149. That's a going in thing. 14% or 1.4%, 1.5% have cancer. That's
Okay.
given.
Mm-hmm.
So that's a given. I think the question that you're probably struggling with is what's the probability of having cancer given that it was negative?
Mm-hmm.
Given that your test was negative, what's the probability of having cancer still?
Okay. Oh, okay.
Well, see, we can figure that out. So it would do the same thing. The probability of having cancer, 0.0149 times the negative test result, 0.2. So we have 0.2 times that divided by, in the numerator, I would have that same thing plus the negative here, 0.9851 times 0.9.
Okay. So it's just opposite.
Yeah, that's going to be a pretty small number.
Yeah.
But it's still a number,
Mm-hmm.
and you don't want to be in it.
I already have been.
Oh, I'm sorry. Oh, oh. Everything okay?
Yeah, it is now. Yeah, thyroid.
Oh, good. Very,
Yeah.
very happy for that.
Thanks.
Yeah. I don't know if these numbers are actually real, but they might be.
Uh-huh.
These two, but I don't know about these.
Mm-hmm.
I probably made these up.
Okay. That did actually help.
Yeah. Yeah, if you do it the other way.
Mm-hmm.
And so you can envision a tree diagram. Let's go back. Oh, not here. Let me get the PowerPoint back. Can you still see the PowerPoint?
Yes.
I'll do that. Is that on the tree? This one. Oh, it still only has 2 different endpoints here. I was trying to find one with 3 different endpoints. We've got 3 here. So this was so the probability of a man having cancer, period. How would you do that? What's the probability of a man having cancer? One of these cancers. Well, it would be 0.44 times 0.15 plus 0.63 times 0.41 plus 0.2 times 0.44.
Mm-hmm. That makes sense.
That's the probability of it. So yeah, because these are all of the conditions.
Mm-hmm. Okay.
So just to take this a step further, and I hope I don't confuse anybody, if I was to add up what you just did with all the men that have in all the men in the chart, and then I also did a separate one and added up all the women, should that add up to 100%?
Well, I'm reconsidering what I just said, to tell you the truth, because I start with 100% of the people having cancer.
Yeah, that's what. So wouldn't we just add each of the men's?
Yeah. Well, you can't just add them, because if you added, no, because if you have to still add 4 times 15. Yeah, you still have to add it, right? Right. No, you multiply these numbers together and add them. 4 times 0.15 plus 0.63 times 4.1. That's the probability that a man would have cancer. The probability that a woman would have cancer would be the other side, 0.56 times 0.51 plus that, and then plus 0.37 times 0.41, etc. Those 2 sums should add up to 100%.
Okay, that's what I was thinking.
That's a great question.
Yeah.
I used to teach math, so I seeing the relationships and taking it a step further helps me understand it in simpler terms.
That's the best way to do it. If you can do that, I applaud that. But it's 100% because I started with 100%.
Right.
So if this were the percent of the population that have head cancer, so this might be something else, then this whole total would not be 100%.
Okay,
Whatever.
but
Yeah.
Okay.
So then would we actually be then saying, since we're starting out with 100% of the people here in this chart have cancer, wouldn't, by multiplying and adding up, wouldn't we actually be stating more of, given that they have cancer, what percent of them are male?
Yep.
Okay.
I was hoping that's where you were headed. Yep.
Okay. Okay.
What percent are male?
Okay.
Right. That's what you would get. So you can get that by, you can go through a thought experiment And just think of this as 0.1 or 0.01. Just think of each man as being small, each number being small. And so the total percent of men would be small then compared to the women. And you can see that would give you the percent of men having cancer. I mean, it's a little more intuitive, I think. So when I do my thought experiments, I always try to go to an extreme case. Take the extreme case, they all have cancer. They're all men. No women have these cancers. So then this would add up to 100% for the men. Uh-oh, didn't sound like I struck any bells there.
No, I'm with you still. I'm still with you.
Okay,
Thank
good.
you.
Yeah. All right. Great questions, ladies. I love it.
Hello, Professor.
Yes.
I have a question about the Excel project.
Okay.
On the actual Excel document itself, it says justify your answer to question 7. And on the printout, it says for number 9, it seems like, I guess I'm unsure which question's being asked of us to fill in, because the number 9 question on the printout says, do the data supplied and the calculated values found in 2 through 5 show that getting good grades on the quizzes will result in good exam scores? So I took that to mean, all right, looking at the coefficient of determination, showing what that number was and showing, well, actually, it's not a good predictor and there probably are other things going on. Did you want that kind of answer, or did you want more of a...
No, that's exactly right. That's right. It is there. That data point does not indicate that there's a relationship.
Right. I think it was 50 something percent. But okay, so you didn't want me to go through how I understood the equation itself.
No, I don't need you to detail the mathematics. Interpret the mathematics is what I'm looking for.
Okay.
Interpret
Well,
it.
that's
Yeah.
answered my question. All right.
Good.
Thank you.
Yes, thank you. Any more questions?
Hi, Professor. This is Myra. This question was regarding our quiz 7. I'm not sure this happened to anyone else, but for my grade, it says that the score was manually adjusted. So I received a 0, even though I completed the quiz. I don't know if that's just me, though.
What?
Yeah, so on quiz 7.
Yeah, no, I understand what you said, but
yeah. Okay.
I'm having a hard time with this one. So grades?
Yeah.
Quiz 7.
I received a grade of 0, even though I completed it.
Yeah, right.
For number 7, chapter 7.
Right, and you're Myra?
Yes, Myra. Right there, under Monica.
Oh, Myra, there it is.
Yes.
Oh, you can see this?
Yeah.
Oh, okay. I thought you could only see the PowerPoint things. Oh, okay. I'm sorry. Well, I certainly believe you. Oh, I wonder what happened here. I don't know how these got shaded in. Well, I do know how they got shaded in. I hit a button and simultaneously something happened that shaded in several of these things, and they're all zeros. I'm going to have to look into that. I asked, and one lady said, no, they won't hurt anything, but I'm not believing it. Myra, you're the only one with a 0.
No, it looks like there's other people with zeros for chapter.
No, I know, but I mean, right, but everybody that's shaded in has a 0.
Yeah. But just wanted to tell you because I didn't want the email to get lost or in the forum lost.
No. Okay, so let's see here. Shaded areas, okay. Now, this quiz is closed, I presume. Is that true? I presume quiz 7 is closed?
Yes, it's already been closed. It closed, I believe, on Monday.
So do you know what grade you had?
Yeah, I had a 15.
15?
I can
Are
send
you
you.
sure?
Yes, I can send you a screenshot.
Okay, you had a 15 on quiz 7, okay. On quiz 7. Wow. Well, I'll see what I can do. I can probably change the grade right away.
I'll send you an email with the screenshot just so that you know.
What's that?
I can send you an email with the screenshot of the quiz results.
No, that's okay. I have enough emails.
Okay. And then I also had another question regarding the next exam, exam number 2. I was just wondering, is it going to cover everything just between exam 1 and 2 or
Yes,
up
yes.
to 2? Okay.
Just between 1 and 2. And
Okay.
exam 3 is just between 2 and 3.
Okay, all right.
And exam 3 is equivalent to our final, like there's no cumulative final.
There's no cumulative final.
Okay, so we have the 3 exams, the quizzes, and whatever else is on our syllabus for grade-wise.
Excel project.
Okay.
15 she says. We'll see if that stays 15.
You can still see all of our attempts, so if anyone else has this issue, there's... Because under the quiz, it said something about my score will be manually adjusted. It didn't highlight like in blue after we finish our attempts. One score will be highlighted in blue, which is the highest score. So when I finished the quizzes and it closed, there was no score that was highlighted. It just stayed at 0, even though I completed multiple attempts and had different scores. There was no score that was like, this is your highest grade for quiz 7.
So you never got a grade in that box?
No, there was no grade, even though I could see the history of my quiz completion. Like I had a 7 and then a 10 and then, let's say 2 11s and then finally 15. None of them filled in the grade score, even after the quiz was closed, if that makes sense.
Yeah, it does it doesn't make sense, but I understand what you're saying.
Okay, all right.
Yeah. Wow, that's interesting. So this hasn't happened to you with other quizzes?
No, it was just quiz 7 because I was checking the results and it just stayed at 0.
Yeah. Everybody else on quiz 7, there's lots of positive scores there. So can you check your grade now and see what it says?
Yes, I will check right now.
It should be a 15.
Professor, while she's checking, can I ask one more question about the Excel project?
Yeah, sure.
You had us do the regression line in the form E equals A plus BX.
Y equals.
And I had it as Y and X because that's what we've typically been using.
Right.
But on the Excel thing, it prompts to have the equation of the best fit regression line in the form E equals A plus BX, where X represents total quiz score and E represents average test score. Do you want us to follow the format there, or is it okay if we put Y?
Y is fine.
Y is fine. Okay.
Thank you. That's going. That might. So the E was from my Word document.
Mm-hmm. Yeah.
And that's a typo or something. I don't know how Y and E get misplaced. I
didn't know if that was another standard form of expressing that equation that I hadn't seen in the book or in your.
I think that it probably stands for expected value. This is what you would expect to get.
Right, the predictive function of it.
That's the predicted value that you would get.
Okay.
Right.
Oh, I checked. So yeah, it finally updated.
Good.
Thank you, Professor.
Yep, you're welcome. Got rid of all those things. All right. Anything else? We're quiet. We're gonna.
It was very helpful. Thank you, Professor.
You're welcome. I'm happy to do it for you. It's been-
Yeah, if I don't know if it will help other people, but I really like the format of us being prepared beforehand and coming and going through the slides again with you live. That really, really helped me.
I think
helped me
coming
too, I agree.
prepared is so powerful. I think that's so powerful.
Will you be posting this live chat?
I am going to post it.
Okay.
Matter of fact, I'm going to cut it off now, I think.
Okay.
I think we're
Okay.
probably done.
Have a good night, Professor.
You have a nice
Thank
night
you.
too. Thank you very much, ladies.
Thank you. Good night.
Good night.
Thank you.
Thank you. Goodbye.
Goodbye. Where is this thing here? CC, go back to this. Where's my meeting?